Hi everyone, this is Krishna Mulugupati, working as assistant professor in Triple Department, St. Peter's Engineering College. Here in this lecture, I am going to discuss about power electronics. In the last lecture, I have given the basic introduction of power electronics, scope, and the applications of power electronics, and different converters, different power modulators, what we are using for power processing also been covered, and I also discussed this whole syllabus of power electronics in the previous class. I already told that entire syllabus of the power electronics involves all four different types of power converters apart from the different types of switching devices. So in the last class we have seen only those things. In this class, we are going to discuss the definition of power electronics and advantages, disadvantages. Apart from these two, we are going to discuss the different switching devices, what we call solid state devices, which are using for high power applications. Okay, let us see the definition of power electronics. See this, power electronics is a power processing unit which is used to process the and control the electrical power. So I already given the details about the basic signal level electronic circuits and power level electronic circuits in the last class. So that's why I am not repeating that. I am directly going to the power handling electronics. Okay, so that's why this is becoming power electronics. And when we see the block diagram of power electronic circuit, these are main power electronic circuits in which we are going to use the different types of configurations based on the requirement of load. And we have the power source. Basically, we are having AC power source, DC power source. AC in the nature available like a three-phase supply and single-phase supply. DC when we are using different types of batteries. So, and DC power is not a direct power, just to be converted from AC nature. Only because of the AC only going to be generated in the generating points, but that has to be converted into DC powers and it is to be stored in batteries. One more information is that AC we couldn't store. Whatever the AC generated must be utilized at that particular time. But when you convert that AC power, AC electrical power into DC electrical power, we can able to use that DC electrical power in other timings. Means what? We are going to converting that AC power into DC power and stored in batteries and utilizing in some other timings for different applications like that. So as I said, as is given in the definition, power electronics is a power processing unit. Here we are going to use the power processing unit, PPU shortcut. So in this power processing unit, this what does it do is it's going to be processing the power. And when you see there is a control unit which is going to be controlling the output values and giving back to the PPU circuit, so that whatever the differences are there going to be controlled here itself in the power electronic circuit. Thereby it's going to be processing the power from load to load, and it's going to be controlling the values what the load requires. Like that, the power electronic circuit is a power processing unit which is used to process and control the electrical power. So, for example, when we take phase control rectifier, what we call the rectifier, which is used to convert that AC power to DC power. In that case, when you use the rectifier circuit, when we use the thyristor or SCR, silicon control rectifier. Basically, silicon control rectifier is a three-terminal device in which we can able to find anode, cathode, and gate terminal. Extra terminal is called gate terminal. Here, the gate terminal is called controlling terminal. And it is going to be controlling the output of the configuration. Okay, so rectifier, when you use the thyristor based rectifier, it's going to be controlling the output of this configuration and process the power from load to source to load. Like that, we have the different types of converters based on the configuration that we are going to incorporate. And these are having these power electronics having both advantages, disadvantages, merits and demerits. We will see the advantages. Mechanical losses, I am saying zero. Why I am saying mechanical losses zero means there is no rotating part in the power processing unit. When you take the DC generator, which is used to provide the DC supply to synchronous generator to excite the field winding, there we can call that DC generator is a rotating machine. Then what happened? Rotating losses called mechanical losses are presented in the operation. But when you use the this type of power electronic circuits, means to convert AC supply into DC supply, only there exist switching losses, very less switching losses, because of absence of rotating part in the configuration. Thereby, I can say mechanical losses are zero. And switching losses are also very less, because if you use the single phase thyristor circuit or if you use the three phase rectifier circuit in terms of SCRs, then there exists around 6 SCRs. Each one we can say 1 volt, 2 volt drop will be there across them. Thereby, when you compare with the kilovolt values, the values which are going to be dropped across the SCRs, you can consider them as a very less value. That's why I'm saying switching losses are less when you use the power electronic configuration. And we can say there is no mechanical losses. There is no very less switching loss there when you use the power electronics. Can I say if the losses are very less, can I improve the efficiency? Means I can get more output power. I can get more output power. As we know, the input power is caused to produce both output power and losses. When losses are reduced, means then we can get more output power where the output power is related to the efficiency directly. That's why we can say efficiency is going to be increased or improved. Thereby, you can say efficiency is high when you use the power electronic circuits. And when you compare with the rotating machine or any other machine which is used to convert the one form of electrical energy into other form of electrical energy, the size that is going to be occupied by that particular machine or equipment is more. That's why when you use the power electronic circuit, the size is going to be very less, compact in size. For example, when you take the DC generator to convert that to supply DC power to the synchronous generator to excite the field winding. So we have to provide more space to place the DC generator there very near to the synchronous generator. Suppose when you use the power electronic circuit, means rectifier bank there. So as compared to the space required to that DC generator, the space required for that rectifier bank is very less. I can say that's why the size of the rectifier circuit is going to be very less and occupies very less space. So these are the few advantages that we can discuss, and some are there. And apart from the advantages, we have the disadvantages also. So main disadvantage of power electronic devices, as I said, Power electronic device is nothing but a semiconductor device. It's nothing but a semiconductor device. As we know, semiconductor devices are related to the um, what we call negative temperature coefficient devices. Negative temperature coefficient devices and producing the non-linear characteristics. Producing the non-linear characteristics. Not only that, so one major disadvantage when you use the power device is it produces the harmonics in the system. Harmonics in the system. So harmonics are very dangerous when they are there in the system. What do you mean by harmonics? Harmonics means the fundamental value and the multiple frequency values are presented in these signals. Not only fundamental value and the multiple frequency values of fundamental values of produced. You can say that signal having the fundamental frequency apart from the harmonic values also. Means let us say fundamental frequency is F and H. Harmonics will be developed apart from the fundamental. We can call that as 3F, 5F, 7F, 9F means odd harmonics. Apart from the odd harmonics, sometimes even harmonics also presented. So you can say when you use the power devices, harmonics are more, which will damage the system. So for the general statement that the IEEE has given to us is whatever may be the system, whatever may be the theoretical system, there must be less than 5% of harmonics only present. So not more than the 5%, there must be not any harmonics. Then only the system will be very healthy. Otherwise, you have to see malabsorption takes place. Then, when we see these, iron losses are increased. Iron losses are increased means because of presence of harmonics. Harmonics are in terms of frequency values, different frequency values, higher frequency values. Means we can say iron losses are depends on frequency of the signals also. So that if the frequency in the system increases means indirectly saying that iron losses also there, iron losses also increase if any iron materials are going to be used in the operation. Generally what happened is in the operation we can say iron losses are constant. When we are analyzing any machine, we are taking once only the calculation of iron losses. But when you use the power alternate devices, the disadvantage is iron losses are not constant losses, those are going to be variable losses. That's why you can say iron losses are increased in this case. And more important one is more heating effect will be there. More heating effect will be there. This is also based on frequency again. And because of this more heating effect, whatever the Paratron configuration, which is used to convert the electrical energy from one form to another form, is going to be damaged. Entire power circuit is going to be damaged after reaching to its rated temperature values. Okay, they're producing nonlinear characteristics. Some more points are there. So, like this, we can say advantages, disadvantages. And apart from these, we can see switching devices. Switching devices. The switching devices are, you can see here on the board. First one is power diode, which is not like a normal diode. I will give you the details why these two are different from each other. And SCR, SR is same as normal SCR, but the doping levels of this SCR are going to be different. So when we see the SCR topic, we will discuss more about this. Power BJT, power MOSFET, power IGBT, lastly GTB. See, in all the cases, these are the main devices which we are using in our power electronics to convert the electrical energy from one form to another form. Okay, now all different types of devices we will take one by one. First of all, we will take a power diode. In the every device, I am going to discuss few things. First one is basics of power diode. Then types, if any types presented that particular device, types of power diode. Then third one, symbol, symbol of power diode. Then structure, very important one, structure of power diode. Structure of power diode. Then lastly we will see few applications. Applications. Power diode. Okay, we will see basics. So basics of power diode. So we will discuss few points about the power diode. So basically, we have to show the difference between the normal diode and power diode, because this power diode must be handle the high powers. High powers in the sense in terms of megawatt, not in terms of milliwatt. Milliwatts normal diode is for the carrying the milliwattage, but in this case, power electronics, we are going to use the power diode for handling the megawattage of power. That's why we have to make some changes. So in order to increase the power handling capacity of the device, so few changes are made in normal diode structure, and perform it. Power diode performs different types of operations when you use in the power systems or use in the conversion of electrical power. So let us see one, for example, power diode using in conversion of AC power into DC power. It's very easy. This we are going to use different type of power diode. We are going to see types of power diodes after this, and we can use this power diode for converting the AC power supply into DC power. And it is one more advantage of this power diode is it has a high switching speed. High switching speed, one of the advantage of this power diode, and it is having a high reverse recovery characteristics. Means suppose when you on the device, generally what happens in case of power in case of semiconductor means, so once the device on, it takes time to come back to the off state. So, but what happened in case of power diode, we made the structure like that, that the characteristics that the device having like this, high reverse recovery characteristics. As soon as we need to stop the operation, the device must be come back to off state from its on state. That the one of the property of this power diode is that. So, when we see the different types of power diodes, there exist three different types of power diodes which we are using in power electronics. The first one is general purpose PN junction diode, and it's same as our normal diode, but doping the levels of this PN junction diode is different. The fast recovery diode, Schottky diode. So these are all common in normal diode also, but when you use for the high power applications, we are going to give more doping values. So when we see this general purpose PN mentioned there, this is basically using for low power applications like a rectification purpose, where we are going to convert the AC power into DC power. This type of PN mentioned diodes are going to be used in the operation, and it having the high speed switching values means as soon after of the operation, then immediately come back to the forward blocking mode. And this type of fast recovery diodes means the reverse recovery characteristics are more for this type of fast recovery diode. Means what? It takes a very less time to come back to off state, recovery state. And these are used for mainly in terms of high power applications called inverting operation. Inverting operation means which we are going to convert the DC power into AC power for different applications. In that case, we are going to use these fast recovery diodes. And coming to Schottky diodes, Schottky diodes are specially made to high current, low voltage type applications, and this will going to be handle the voltage values means breakdown voltage values like from 50 volt to 100 volt. In between, it is going to be breakdown very easily, and it is used for high current carrying purpose and low voltage carrying purpose. As I said, using for high current, low voltage like UPS systems. UPS systems nowadays are very popular. In that case, when there is a need of using of power diode, the Schottky diode is going to be used in that. Coming to structure of power diode, when you compare with normal diode and power diode, see clearly. See, this is the structure of a normal diode. One p-type material, one n-type material being sandwiched together and forming one junction here. Okay, it's for signal level applications. So when you go for a power level application, the same structure is modified, means doping levels of p-type and n-type are being going to be changed here. Look at this structure of power diode. Just you see, this type and this type is very compact in size, but doping levels are very less. So because of handling the milliwattage of power, millivolt, microamperes to milliampere level. But in case of this one, it has to be handled voltage from few volts to few kilovolt level, few amperes to few several kiloampere level, like that megawattage of power level. That's why the structure of power diode is going to be modified like this. Look at this. This is p-type material, p plus n minus n plus. So very simple. N minus n plus indicating what? Doping level. P plus means it is p-type material basically. This p-type material is highly doped one. P plus means highly doped. This plus indicates the highly doped material. See, this is the structure. This one here we are found. We have the junction point. This is junction. When we sandwich two different types of materials together, there exists one junction in between the two materials, as we know that. So this is the junction formed in between these two, what we call the depletion layer of the device. The depletion layer of this device is more and more. The width of the depletion layer is very high here in this case. Okay, the size, when you see the size of this p-type material is 10 mm size only. This region is only around 10 mm size, occupied 10 power 19 cube centimeters. Okay, then when you see the n minus means this is what we call drift layer. N minus layer is called drift layer. You can see that WD, this WD, the width of the drift layer means which is used to help to help for the breakdown voltage values. Suppose you want to change the width of the breakdown, this n minus layer, automatically what happened? The size of the width, when we change that, automatically breakdown voltage levels also been changed. So entire breakdown voltage levels for the device based on the width of this n minus layer. And when you see the n plus layer means what? This portion of the n material. When you see this is totally n material, this portion only p material, and in this portion, in this total n material, this total part is lightly doped. N minus means what? It is lightly doped and it's having 10 power 14 centimeter cube. Okay, and the below portion of this N material is going to be highly doped. Here the entire portion is highly doped here, and the size of this highly doped N material part is around 250 to 300 mm. So very easy to understand. This is the normal diode to handle the signal level application. This is the power diode to handle the high power applications, to use in the high power applications. Let us see the symbol of the power diode. The symbol of the power diode and the symbol of the normal diode, both are same. There is no difference. So look at this. This is the symbol of power diode. Then characteristics of power diode, when we see, these are same as a normal diode. So we'll take one diode. This is my diode. I'm connecting different biasing voltages. So different biasing voltage. This is biasing voltage. Biasing voltage. Based on the voltage that I am applying to the device, it decides the operation of the characteristics of the device. Basically we can call that as a static VI characteristics of power diode. So I am taking the characteristics like this. So on y-axis I am taking current which is flowing through this device, and voltage applied across the device like this. Okay. So suppose there exists two modes of operation for the diode. So when I am using voltage or battery here, DC supply here like this, means positive is connected to the anode, negative is connected to the cathode. Positive is of the battery is connected to the anode of the device, and negative of the battery is connected to the cathode of the device. This type of biasing is called forward bias. This type of biasing is called forward bias. In this case, what happened? The junction, there exists only one junction. There is after applying this type of supply to that device, we can say first quadrant operation comes in the action. So this is a positive value. This is a positive current values. So as we know, this is not a conductor, it's a semiconductor device. That's why. So on producing the non-linear characters, due to that what happened, after applying immediately doesn't give any conduction, takes some drop like this. So junction has to break down and producing the characters like this. This point is called forward break over voltage. Forward break over voltage is what we call. Means this is around for the power diode it's around 5 volt. 5 volt to 6 volt for the power diode. When you see the normal diode, what happens is it is around 0.6 for the silicon, 0.7 for the germanium, like 0.5 and 0.7 means less than 1 volt will be there, the drop voltage across the normal diode. When you compare with the power diode, what happened is, because of we are applying voltage to kilovolt ampere, kilovolt voltage levels to that power diode. Due to that, what happened? The drop value is increased to 5 volt. So it can withstand with 5 volt. After that, it's going to be coming into conduction state, means allow the current to flow through the device like this. Current is entering like this, back to this way. This biasing I already told that the forward bias. After that, what I am doing is I am simply changing the biasing like this. Now this is plus, this is minus. Means I am changing that positive terminal, positive of the battery is connected to the cathode of the device, negative of the battery is connected to the anode of the device. This type of biasing is called reverse biasing. In this case, what happened? We are getting the third quadrant operation, means negative voltage is applying across the device so that the current will flow in the reverse direction to the device. So instead of like this, we are getting current like this in this case. That's why we are getting this value. But what happened here? In this case, junction width is going to be increased a lot. Junction width is going to be increased a lot instead of a breakdown. Then what happened? After applying some voltage, what we call here reverse breakdown voltage. Reverse breakdown voltage. Then only there exists avalanche breakdown across the junction and junction breakdowns. But what happens in case of this reverse biasing? Reverse biasing is very dangerous in case of diodes. It doesn't allow the operation during negative voltage applying across the device. That's why. So before this value only, we can stop the operation. Otherwise, what happened is avalanche breakdown occurs. The voltage which we are applying across the device will try to damage the entire device also. That's why don't try to apply reverse voltage across the diode, which is going to be damage the device. Look at this. During this process, we are getting some current values. This current value is called leakage current value. Leakage current. Leakage current. And leakage current is mainly due to minority carriers in semiconductor devices. In this operation also, in forward bias also, we are having some leakage current during forward bias condition also. Okay, let us see finally applications of power diode. Applications. Mainly these are used for low power applications like rectifiers, and for freewheeling action. Freewheeling action, we are using only diodes. No other semiconductor device is available in power electronics for freewheeling action. That's why we are using for freewheeling action. Freewheeling action where it is required in the operation. Freewheeling action. And all in DC-DC converters, DC to DC converters, then AC to AC converters, then DC to AC converters for inverters, DC to AC converters, finally, as I said, when you use this Schottky diodes like that power diodes, it will go for UPS system. UPS system. Okay. So in this video, we are seeing the definition of power electronic, basic definition of power electronic, and its block diagram. Then after we have seen advantages and disadvantages, merits and demerits of power electronics circuits. After that, I have taken switching devices. Switching devices are we have power diode, SCR, power BJT, power MOSFET, power IGBT, GTO like that. So in this video, we have already seen the power diode and power diode basics, power diode um, structure, power diode symbol, power diode types of power diodes, then characteristics of power diodes, application of power diodes. In the next video, we will see the next switching device, SCR. SCR plays vital role in power conversion operation because many applications are we are using in case of power conversion based on the SCR. SCR because of its different characteristics based on its characteristics based on its property. So we are more using the SCR in power conversion applications. Thank you.